Hi, my name is Jessica Bo, and with my co-authors, Pan Hao and Brian Lim at the National University of Singapore, we will be introducing our work, Incremental XAI, Memorable Understanding of AI with Incremental Explanations. Let's start with a case study. We have some houses, and we train an AI system to predict their sales price. The AI system is accurate, but has non-linear internals that makes its prediction-making process complicated to understand. How can we help end users understand how the AI makes predictions across different instances, such as houses of different prices? Explainable AI, or XAI, aims to simplify AI systems to make them more transparent and interpretable. In our case, we aim to increase the user's understanding of memory of how the AI makes predictions via explanation, so that users can quickly recall and apply the knowledge for downstream decision-making. We focus on post-hoc explanations of black box models and provide explanations via simple linear models, which indicate the weight of the contribution of each feature. Let's take a look at the explanation interface. Here, we have the attributes and their values, and the temperature bar shows the relative magnitude of the values, so this house is relatively smaller than the others. These are the linear factors. They explain that the AI system approximately weighs each bathroom to be $17,000, each kilo square feet to be $150,000, and so forth. The next column shows the partial price contributed by each attribute, which is the value multiplied by the factors and summed. The adjustment corresponds to the intercept that gets added to the partial prices, finally producing the AI explainer's estimation. The real prediction made by the AI system is also shown with the error rates. We apply the same explanation to the larger house. However, as we can see, the error of the explainer is bigger, which means that the explanation does not fit to it as well. The linear factor explanation, which we call a global explanation, is overly simple and has poor faithfulness, or accuracy, to the non-linear AI system. The faithfulness can be improved by partitioning the dataset into two subspaces and fitting separate linear models. We call this a subglobal explanation, and it does achieve higher faithfulness. The subglobal explanation has the same structure as global, but notice that the factors are different in the two subspaces, which are partitioned by the living room being below or above 2.5 kilo square feet. The error of the explainer is also much smaller for both houses. However, memorizing multiple set of factors becomes challenging, so the subglobal explanation does not scale well. We wish to minimize the number of additional factors while maintaining the faithfulness, so we define the factors in the second subspace to be built upon the factors of the first subspace and make them as consistent with each other as possible to reduce sparsity. This creates the incremental explanation. Let's have a look at an example. The interface is expanded to accommodate columns for two sets of factors. For the smaller house, only the general factors apply, while the additive factors are all 0. For the larger house, since the living area is 3.2 and greater than the threshold of 2.5 kilo square feet, the general factors are modified by a set of sparse incremental factors. For example, the factor for bathroom does not change, but the factor for living room is increased by 120,000. The error rate is similar to subglobal, but the number of factors is reduced for memorability. As a high-level approach to explaining AI systems, we make an analogy to how humans learn. Users are first taught to understand the AI system generally, and then they can build on top with more detailed explanations for special cases. Analogously, in physics class at school, students are first taught general rules about physics, like Newtonian laws of motion. Then once a student masters the basic concepts, they can progress to complex topics like special relativity, which build on the general rules with additional special rules. The technical details of Incremental XAI are explained as follows. Given an AI that makes prediction y hat from a feature xr, we want an XAI that models the AI faithfully. Incremental XAI first partitions the dataset into typical and outlier subspaces. The general explanation applies broadly to all instances in the input space, but the special explanation applies additively to only the special outlier instances. How is the partition threshold selected? We use a linear tree model, which works like a decision tree, except the leaves are linear models that best fit to the data in their group. A linear tree with a depth of 1 creates 1 partition and 2 linear models, which is equivalent to the subglobal explanation. For the incremental explanation, we adjust the factors so that the second model is based on the first, which I'll explain next. The linear tree can select the optimal interpretable partitioning threshold, which turns out to be living area for the housing dataset. And note well that this method is automated, we also allow users to select custom thresholds to fit their personal explanation needs. Now, we take the linear model factors generated in the previous step and tune them with gradient descent using the objective equation described here. The first term is a mean square loss, which optimizes faithfulness to the AI, and the second term maximizes subspace consistency and sparsity by making the delta W, the difference between the general and the special factors, as small as possible, which pushes some of the terms to 0 to induce sparsity. For our experiments, we benchmark incremental against global and subglobal, which we described previously. We also introduced the local baseline implemented with LIME, which only explains small local neighborhoods of data. Local techniques are highly popular for explaining specific instances, so we include it due to its ubiquity. While local is very faithful, its explanations tend to have very high variance across the input space, so it's difficult to draw a general understanding of the AI system's overall behavior. Therefore, we hypothesize that users will have a harder time applying it to unseen instances. We performed 3 experiments. First, the modeling study, which compares faithfulness across all the XAIs. Second, the formative user study, which looks at the qualitative user experience and perception of the XAIs. And third, the summative user study, which quantitatively measures users' performance in memorizing and understanding the AI system via using the XAIs. Now let's look at the results. In the modeling study, faithfulness is measured as the mean average error for each XAI and reported separately for the typical subspace in red and the outlier subspace in blue. For generalizability, we conduct the analysis across 3 datasets: housing price prediction, heart disease risk estimation, and auto MPG estimation. Across all datasets, incremental and subglobal achieve similar levels of faithfulness, striking a balance between global, which is much worse, and local, which is better. And what about memorability and comprehension? We conduct the user studies next. In the formative study, we recruit 14 university students as participants who learn the XAI interfaces with the housing price prediction task and report their experiences. 2 key insights were observed. 1, people perceive incremental factors to be more memorable than subglobal, stating that incremental is more informed since it tells you how the factors are changing, and that incremental has fewer numbers to remember. 2, people also believe that factors that change between instances have higher utility, stating that it's not realistic for factors to be the same for all houses, such as they are in global, and that the additive factors of incremental led to a perception of improved accuracy. We also use the participants' feedback to improve the interface design. Next, we test how people perform in tasks with the XAIs. In the summative user study, we recruit 160 participants from Prolific, measuring understanding and memorability. Understanding is the ability to simulate the AI with and without the help of the XAI. And memorability is the recall of the explanation factors and the decision time to simulate the AI, which we consider as an indirect evocation of the XAI. The procedure starts with a tutorial of an XAI and screening questions to ensure that the participant is well trained. Then the participant went through 25 forward simulation trials, aka predicting as the AI. And this is split into 3 sub-steps to enhance learning. First, simulate the AI without the XAI. Second, simulate the AI given the XAI estimation. And lastly, review the correct AI predictions. Next, depending on their condition, the participants had to either estimate or recall the factor that best applied to all instances in general or instances in the typical and outlier subspaces. Lastly, the trial ended with a survey of the perceived helpfulness and ease of use of the XAIs and a report of their demographics. We measure supporter understanding as the forward simulation of the AI with the XAI. I find that incremental, subglobal, and local achieved the lowest rates of error compared to global, which reflect the faithfulness of the XAIs. Sustained understanding is the participant's ability to simulate the AI without the XAI, a measure of true understanding. Subglobal and incremental had the lowest errors overall, indicating that people retained good understanding of the AI on unseen instances without the explanation present, whereas local's performance fell. Decision duration measures the time to simulate the AI without the explanation, which echoes implicit memory of evoking the explanation. Incremental and global are significantly faster than subglobal and local, and this could be because global and incremental explanations are easier to recall. And combined with the previous results, we find that incremental achieves faster simulation of the AI than subglobal while maintaining the same level of accuracy. Lastly, participants are asked to estimate the factors that best fit to groups of instances to measure overall understanding of the AI's behavior. The first round is all the instances combined, which is best fit with the global factors. Thus, the global condition participants can recall, while the other conditions have to infer the correct values. The second round is factors for typical and outlier subspaces separated, which the subglobal and incremental participants can recall, while the other two conditions have to infer. The incremental group achieves significantly better recall of the adjustment term, while the other explanation factors did not see a significant difference. We propose several directions of future work to achieve generalization. 1. Apply the incremental paradigm to other types of XAIs, such as general additive models and decision rule sets. 2. Extend the experimentation to other domains, dataset, and variable types, such as ordinal and categorical, and the prediction task can also be changed to classification instead of regression. And 3. Since we only evaluate on the direct understanding of the AI, a subsequent step is to evaluate on AI-supported decision-making for downstream tasks. Finally, we leave on a key takeaway. Incremental XAI is a faithful and more memorable explanation for black box AIs, achieved through providing a general set of factors W and an incremented special set of sparse factors delta W. Thank you for your attention, and feel free to reach out to the authors here at the NUS UBCom lab if you have any questions or follow-up discussions.